Welcome back to Physics Lab, the happiest place on earth. We've been dealing with electric currents for a few weeks. You had your practical. Now we're on to something new, and something really fun, actually. Magnetism is our next subject, and it can be a little bit confusing. It can be more difficult sometimes, but it's also something that is fascinating, and it's something that, at least me personally, I've been playing with since I was little. I remember being really small and having my grandparents buy me some magnets, and I just sit there and play with them for hours and hours. So actually, that's kind of what we're doing today. In today's lab, we're going to be playing with magnets. We've got some magnets, and we're just going to be playing around and making some qualitative observations. Remember a few weeks ago when we did the qualitative circuit lab, where we made some observations about how electrical components would interact and how when I wired things together, they would do certain things. We're doing something similar to that, but with magnetism now. We're going to be playing and having a little bit of fun with magnets. And we are going to be doing a little bit of data, I believe, near the end, but for the most part this week is going to be exploratory, where we're going to just expand our understanding and get some intuition about some of these magnetic phenomena. In front of me, I've got some toys. These are magnets. I carry these in my pocket and I just kind of play with them. I've seen videos of, they're made from the same material, but they're designed to, they're shaped so that when you throw them up in the air, they stick together and they spin a little bit, and they make a cool rattling sound. These will sometimes do it, if I can, yep, kind of, a little bit. Fun with magnets. In front of me, I've got a bar magnet. Magnets come in lots of different shapes and sizes. In front of me, I've got a bar magnet. It's bar-shaped, rectangular. Look at that. It's got an N on it, and it's got an S on it. I got another one. Same thing. Got an N on it on the side in the red, and an S on it on the blue. Any idea what those stand for? You guys probably have an idea what those stand for. In your life, I'm sure you've come across magnets. What is the N and the S?
North and south.
Yes, I think that it's a pretty safe assumption that the folks watching this video knew that already. We got a north side of a magnet and a south side of a magnet. I also have a compass. Those also have a north and a south side on them. Is there a relationship between those? Maybe you never thought of it before. Maybe you have. In my class, we're going to talk about this a lot. But a compass also uses the idea of magnetism. It is, in fact, a magnet. We're going to talk about that today. We're going to use a compass to map out magnetic fields. Remember, we've been talking about electric fields a whole bunch. Magnets have fields, too. Magnetism is also a field force. So we're going to be exploring that a little bit, too. So you can see them here. Now, that compass, the red side is pointing that way, and that way, if I pull out my phone, that way is north, according to the compass on my phone.
Huh.
How about that? So, it's wiggly right now, but the red arrow on that is pointing north. Now, you notice it's not exactly pointing north, though. I wonder why that is. Well, I'm just going to bring, whoa, what just happened there? Can you see that? There's a little glare. Hey, what's going on here? I thought compasses pointed north. Professor Ashcraft, explain what's going on here.
Well, the compasses measures the magnetic field. Kind of like if you have a wind socket, measures wherever the wind is. But if I go out and I have this huge fan, and if I put the huge fan out into the field where the windsock is, it's going to measure whatever the airflow is. It may not measure the wind, it'll just measure the gross airflow. So if you put a big old magnet next to a compass, it's not going to measure the Earth's magnetic field. It's going to measure whatever magnetic field is out there.
Yeah, that makes a lot of sense. So it's measuring the biggest magnetic field around, right? If there's nothing else, the Earth's magnetic field is going to be the biggest magnetic field around. It's going to align with that. But if I bring a bigger magnetic field nearby, it's going to measure that instead. Or since fields are vectors, it's going to measure the resultant force of those.
Yes.
But if the magnetic field from this is substantially bigger than the magnetic field from the Earth, the effects are going to be much bigger from this one than from the smaller field that would measure otherwise.
So we add them vectorially.
Yes, we do.
But that only shows you the direction. It doesn't show you the magnitude.
That's true.
Huh. Well, a windsock sometimes just shows you direction too. Or a wind vane does. Sometimes the sock will extend itself.
Sure.
Okay.
So the first part of this lab tells us to do what we're doing right now. It says get your magnets out, get your compass out, and just play around. So let's do that. I'm just going to mess around here under the camera. Okay, so I've got my little magnetic rocks, magnetic hematite, I believe. Hema, doesn't that, like, that sounds familiar? Like, hemoglobin is in your blood?
Iron.
Ah.
Yes.
Another way to say iron is ferrous or ferro.
Right?
These types of materials that can be magnetized are called ferromagnetic materials, and one of the major ones is iron. Iron, nickel, and cobalt are pretty common. So iron is important. It's an important ferromagnetic material.
There is a mineral magnetite.
You know where the word magnetism comes from?
Magnesia, where they
Yeah.
make the milk?
In it's in the Middle East, right? Isn't
Yes.
it present-day Iraq, maybe?
Maybe.
In that vicinity?
In that vicinity, yes, sir.
Yep, they found rocks that stuck together, and they're like, whoa, this is cool. And you know what? They were right. It is cool. Okay, so we've got magnetic rock here. This one is kind of neat. It's shaped like a Superman symbol. This one is diamond-shaped. Bring them close together. Whoa.
Whoa.
That was cool. Now, if I put it on the other side, it flipped over and then stuck. So this side doesn't want to stick, but the other side does. So even at a distance, whoosh. Force at a distance is a type of field force. Spun it right around. Really cool. So evidently, this is the south side of this magnet. How do I know that?
Well, what's South attracted to?
No, I have to lean on, because my labeled magnets aren't that strong, I have to lean on my previous knowledge. And I do know that when it comes to magnets, the north side of a magnet is attracted to the south side of a magnet. And the south side of this magnet is attracted to the north side of that magnet. If I try to put the south sides together, these ones are so weak that they're not going to really care that much. But if they were stronger, they would feel a repulsion, just like the rocks did. When I had the two like sides together, it spun it right around.
Hey, you got that multicolored thing right there.
Oh yeah, this thing's cool. So these are magnets too. I can tell because they stick, right? Made a hole. And they're sticking together as well. These come apart, but they're not coming apart. Gravitationally, they're not strong enough to pull apart, so the force that's holding them together is stronger than the weight of the objects and the gravity, the gravitational force. If I flip it over, oh, they are not. They're not sticking. And I can prove it. If you think I'm just a good actor, I can prove it by stacking it up. Look at that.
Can you do that again, sir?
Oh yeah.
Just a second, just a second, just a second. Okay, now I'm ready. Whoa!
Oh, that one's upside down. That one's stuck. But just to prove my point, now it's not stuck. I can push them together. Oh, they do not want to be together. Like,
So, are you telling me there's a north-seeking side and a south-seeking side to, like, that ring magnet? Just like there was on the bar magnet?
yes, I am. So these two sides that we're pointing towards each other do not want to go together. I'm not a good enough actor to pretend. They really don't. Flip it over, they go together really easily. So much so that I don't even have to hold them. They just stick.
Wow.
Cool.
Neat.
So just like the rocks and just like the bar magnets, anything that is magnetic, if it is a magnet, it's got a north side and it's got a south side. There's no such thing as a magnetic monopole. They're always magnetic dipoles. South sides oppose, north sides oppose, and north and the south are going to attract. How about that? Now, we mentioned the fact that these compasses use magnetic fields. The only things that feel the effects of magnetic fields are magnetic things themselves. So that needle inside of this compass right there, it's a magnet. And I know it's a magnet because of how it was interacting with the magnet when I brought it close. And I said that the red arrow, or the red needle here, was pointed in the geographic north. All right? We can prove that, I guess. I did. I pulled the phone over and you saw it. to the direction it's pointing. I bring my bar magnet over. This is the south side. And the arrow that was pointed towards the north geographic pole is pointed towards the south magnetic pole of this magnet. Now, to me, that's kind of mysterious. Because I said that that way is north. And the arrow was pointed that way. The red needle was pointed that way. But on my bar magnet, the red needle is pointed towards the south side. What does that mean? I'm a little bit confused. Shouldn't the needle point towards the north side if it's pointing geographically north? Shouldn't it point towards the north pole of the magnet? It's pointing towards the north pole of the planet. Shouldn't it point towards the north pole of the magnet? It tells me something about the north geographic pole and the north magnetic pole of our planet. So if the needle points towards the north geographic pole,
Right,
but it points towards the south magnetic pole,
right.
that kind of implies to me that the north geographic pole isn't the north magnetic pole for our planet. In fact, it implies to me that the north geographic pole is the south magnetic pole. And vice versa down there. In the south pole, the south geographic pole is the north magnetic pole. We happen to live on a planet, and my geographic skills aren't the best. You can probably identify what planet that is.
Is there Canada?
Yeah, it's just kind of subsumed here.
Okay, all right.
It's not drawn to scale.
Okay.
Planet Earth. And inside of this planet, we're going to talk about this in the lecture, but there's a big molten iron core. That molten iron core is moving around. And in that iron core, there is charged particles, as there are everywhere. And as we will discuss in this lab today, all magnetism, all magnetic fields are associated with moving charges. And we happen to have a molten core that is moving inside of our planet. And that's producing magnetic fields that produce a magnetic field of our planet. Okay, awesome. So it's almost as if one of these things is running through the middle, or close to it. And when I pulled that compass out, the red needle pointed up this way. But the red needle also pointed towards the south pole of this magnet. So to me, that implies a magnet that looks kind of like this. Our planet magnet looks kind of like this. So this is North Pole. This is South Pole. But the magnet that produces that is kind of flipped. But to me, that's just mind-boggling. That's so cool.
So are they, is that the same location as the geometric North Pole?
Not,
I mean 90 degrees north.
it's not at the same exact location. In fact, this moves. And there's an article on the blackboard for the class about, I think it's 2 years ago, how it was moving through Siberia. Yeah,
Well, that is cool.
it is cool.
Okay.
Let's see. Do we have enough to answer those questions? What do you know about magnetism? Well, that you knew already. So what do you know ahead of time? You know a lot. A lot of the stuff that we've just said, you already knew, and that's okay. That's not just okay, that's great. I'm glad you know it. We're going to build off of the stuff that you know. All right, let's try out some of the things mentioned above. Just playing with them. Okay. Okay, we've got compasses in front of us. We did play with them. It does ask us to take the two compasses and put them near each other. If this is a compass magnet and this compass is a magnet, when I put them near each other, they should interact with each other. I'm trying to make sure we get rid of the glare. And look at that. The silver side of one is linking up with the red side of the other. I think maybe I can get a better view of that if I have a bigger magnet, or bigger compass.
Sure.
Big ones. All right, finally. So we can see here, if I can get the glare off there, that when I put two compasses next to each other, the white side of one is attracted to the red side of the other. Even if I put it over here, the white side of one is attracted to the red side of the other. Opposite sides of this compass are attracted to each other. The magnet in the compass needle acts like any other magnet, where the opposite poles will attract. Awesome. Okay, you can answer the question. The needle of the compass is a magnet. How do you know this to be true from what we just did? All right, take the bar magnet, and what happens when you bring the north end of the magnet towards the compass? And the south side of the compass, south side of the magnet towards the compass. What feature, color, shape, or symbol on the compass distinguishes the North Pole from the South Pole? How do you know? All right, that's on you. You guys can answer that one on your own. Now, it says put the compass near the magnet. Set up the bar magnet as shown with the north side on the right and the south side on the left. We're going to put a compass at a variety of different positions around it. Got our magnet, north side here, south side there. We have our compass. We put the compass at a variety of locations surrounding the magnet. One right in the middle. You should have been able to see all those, and you should be able to map that out. That compass, the magnet inside of that compass, is aligning with the magnetic field of this magnet, just like it aligns with the magnetic field of our planet to point in the general directions and give us an idea of what things are going where. What does this activity show about the direction of the magnetic field lines? Again, that question's on you. If it's aligning with the magnetic field lines, you can make an inference. Now, we do have two more activities to expand this into multiple dimensions. This is a plane. I guess we have two dimensions. We can go this way, we can go this way. Professor Ashcraft's going to take over and he's going to talk to us about going to three dimensions. We have two different ways that we're going to model magnetic field lines. One with a plate that has little pieces of metal that become magnetized. That's something we didn't talk about. This thing right here, not a magnet. If I try to stick a piece of metal to it, it doesn't stick. But if I take another magnet, and if I put this piece of metal in the magnetic field, well, it does stick. And then this thing becomes magnetized, and it'll stick to other pieces of metal. It's really obvious when you have low mass things, like their weight isn't going to overcome. So the paper clips don't stick together by themselves. Paper clips don't stick together by themselves. But I put a magnet next to it, and suddenly it is magnetic. So we're going to use that principle of magnetization to show magnetic fields using a plate with a bunch of little metal rods in it. And then we're going to show it not just in 2 dimensions, we're going to show it in 3 dimensions. So that's on you.
Okay, thank you very much, sir. Now, I want to show a couple things too. No, keep it like that. I'll just hop on in here. We can always edit things. Now, before class, I have a couple things that I kind of put together here. Now, what I have is I've got a solid cube. Thank you, thank you, thank you. And in this solid cube here, it looks pretty hairy. What this is this is iron filings. And the iron filings are kind of cool. And it's kind of hard to tell, but what I have is I've got a single magnet inside here. On this side, I've got the red side. If you remember, the red is the north. And on this side right over here, I've got the blue side. And the blue is the south-seeking pole. North-seeking pole, south-seeking pole. And the iron filings, well, originally they weren't magnetized. They were just floating in this. It's a glycerin-type solution. It's thicker than water, so they can float around. And what they did was they kind of lined up in the magnetic field. So you can see that there's a strong magnetic field at one end, and there's a strong magnetic field at the other end. And the magnetic field, I got such a thick finger, it seems to like go this, or maybe does it go, I don't know, it could go either way. Well, you know what, there's a convention, and the convention says that the magnetic field goes from the north-seeking pole to the south-seeking pole. And honestly, with a ferromagnet also, the field is continuous. It goes around in a circle forever. So it goes from the north-seeking pole to the south-seeking pole, and then in through the magnet, back again. So because it is circular, we need to say, okay, where does it start, where does it end, which direction? And that's the convention. From the north, going out, to the south, coming in. Now, I did one more thing, and this was kind of freaky. I did not expect this at all. What I have here is I have a red touching a blue. So I've got a north that is touching a south-seeking pole. Okay, cool. And this is kind of freaky. The north has got lots of field lines. It's got lots of fur, or it has lots of, oh, you see a lot of the shavings fell to the bottom there, gravity. Let's see if, all right, it's kind of falling now. You can see it's falling slow. Well, maybe you can't see it's falling slowly through the glycerin. There, it was kind of falling slowly through the glycerin there. But this magnet was really stronger than the other magnet. So you can see there's a lot of field lines on the north, hardly any field lines on the south-seeking pole. Why? Well, because the one on the left there is really stronger than the one on the right. Oh, that's kind of interesting. Okay, well, since I know that this guy is stronger than that guy, I'm going to use this guy to demonstrate. Oops, in fact, it's so strong it just kind of carried my other magnet out. Now, what I have here, this is kind of neat. It is a, well, how do I describe it? I've got all these little rods inside here. And if I kind of do it like that, they're all kind of going straight across from left to right. If I kind of knock it like this, now they're all going up and down. And what's really cool is I can put a magnet like right on top of them. And, whoa, I don't know if you saw that or not, but the rods right here went from going left to right to, oh, wow, they went vertical very quickly. And these guys kind of went vertical really quickly. All right, now I need your imagination. I need you to imagine that we have a field going from here to the north. Excuse me, we have a field going from here to the north, going out back into the south. A field from the north going out back into the south. Now, probably happened the same on the bottom too. Now I need you to think in a third dimension. I really need your imagination. This is 2D, flat plane. Let's go 3D. There probably is a field coming out of the north. This is coming towards you, going across, and then going back into the south through the magnet. Same thing underneath there. We don't require you to think 3D, but you know what? It does work 3D. If you can do 3D, I bet you can do, if you can do 2D, excuse me, I bet you can do 3D. So, for the questions, taking the 2D magnetic field demonstrators, make a magnetic sandwich. You know what? I'm going to use a stronger magnet. See if that makes any kind of more of a difference. For this one, I'm going to lay it down flat. Oh, I'll make these guys. Yeah, that's kind of random there. Okay, so I'm going to take my stronger magnet.
The neodymium one's right there too.
Yes, that's my strongest.
I see. I see.
Okay, now I happen to know that north is going to be to the left. How do I know that? Well, because I cheated and I did that earlier. Whoa! Now you can see the lines really good. See how these are even tilted, and these are even tilted. Tilted, 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 tilted. Wow. Okay. At least I hope you can see them. Strongest still. Kind of all left to right. Excuse me, I pulled this one off. I pulled that one off.
North is in your left hand, I believe.
And north is towards my left hand.
Oh, sorry, your right hand.
Okay,
I'm mirrored from you, sorry.
no problem. So north is going to be still this side?
Yes, I believe so.
Okay.
You can check it with the bar.
Yes, you are so true. Hey, did you guys see that? God, I love magnets. Okay. Plop. Whoa. And plop. Wow. That's wicked cool. I hope you guys see this. And I'm sorry that you're not here in person, because this is dramatic, dynamic, really, really cool.
And just a whole bunch of fun.
Yeah. For Cub Scouts, this is magic. And it's neat. It's also measurable. Okay. So, identify which is, let's go to the apps, let's go to the lab manual here. In the absence of any other magnets, a compass is going to point along the magnetic field of the Earth. I like to think about the wind. If I got a windsock, it's going to point in the direction of the wind. Identify which direction is north in the room that you're in. Then hold a compass in your hand away from any other magnetic field. Now, what's going to make a magnetic field in this room? All right, magnets, duh. And what kind of magnets do I have? I got this really strong one, I got this fairly weak one, I got this other one right here. I've got all sorts of magnets. But guys, other magnets in this room are the computers, the displays. There are a tremendous amount of magnetic field generators in this room. Okay, so try to get yourself far away from not only the magnets, but also the computers too. Okay. Hold the compass in your hand away from the magnetic field and rotate the compass so that the north points towards the north. So I'm going to clear this stuff out. And I'm going to try to let it settle. Do any of you guys hike? Because if you do hike, and if you ever have like a geological map, they will talk about what the offset of north is. Now for us in the Northeast, the offset of north is hardly any degrees, because the geometric pole, excuse me, the geomagnetic North Pole, I'm trying to do too many things at once, when the maps were made was in Hudson Bay, north of Canada. And so we're just about lined up with Hudson Bay and the North Pole. But if you go hiking in California, then you might have to change your compass about 10 or 15 degrees to find out where true north is. Okay, so I have that there. Good. Now, look at the compass needle. Which end of the compass points in the north direction? Well, the north-seeking pole. Okay, yeah. Given that opposite poles attract, what type of magnetic pole has got to be located in the north? Very good. Okay. Now, ooh, electromagnetism.
Oh, this is fun.
A permanent magnet makes the magnetic field. Yeah. There's another way you can make a magnetic field. Okay. And that's with moving charge. So we don't need iron. We don't need nickel. We don't need cobalt. All we need are electrons. If the electrons move, they're actually going to make a magnetic field. Okay. So this picture here is kind of funky. What it is it's a wire. And the wire is going straight down through something. And if I have a wire going straight down through a surface, if I take a whole bunch of little compasses, so if I pretend there's a wire sticking up out of the table, if I take a whole bunch of little compasses, and if I just put them all around, and again, we're pretending now, I gotta admit, some of these compasses are gonna point north, some of these compasses aren't. Why not? Because they got stored near some magnets. But anyway, let's say they're all pointing the same direction. This is freaky. If I turn power on, I make a current go through here, then all these compasses all of a sudden are gonna start pointing in a circle. Huh? Well, you remember we just saw the compasses point, so if they would come out the North Pole and go into the South Pole, these guys would start going around in a circle. Okay? Well, if it's a circle, then how do we know which direction? Well, there's going to be something called the right-hand rule. You guys are going to be doing it in class. Really quickly, what you do is you put your thumb in the conventional current, and whichever way your fingers go is the direction of the B field. So if the conventional current is coming up towards you, then the B field is going to be going in the counterclockwise way. See how my fingers in my right hand, well, maybe you don't, because the other hand could be blocking. The fingers of my right hand naturally curl to counterclockwise. If my current is going down into the table, then if I put my right hand, the thumb in the direction of current, then my fingers will naturally curl clockwise. So these compasses will go all the way around. It is cool as can be. Well, how can I show you this? I have got something fantastic to show you. Okay, I got a really neat setup right here. What I have is, first off, I got 2 batteries. I got 3 volts going through here. I have no resistance, so there's going to be a lot of current going through. My current from the positive is going to be going along a wire, and then a kind of diagonal wire, a 90-degree wire, another 90-degree wire, and then back to the batteries. I'm wasting a lot of energy, but this is worth it. Okay, I have a compass that is lined up north with a wire. Okay, and what you can see is I'm lined up north with a wire. Well, I just picked it up and I shook it, now it's wiggling. These things happen. All right, now what I'm going to do is I'm going to hook it up and make a current. Boom! Isn't that sweet? What's going on here? What's going on here is not only, well, I told you how it makes a circle. I need your imagination, guys. Right now, I've got a wire instead of coming up through the table. It is, the current is going this way. Well, this is above it. Oh, wait a second. The higher I get away from it, the less deflection there is. There's almost no deflection. If I get closer, more deflection. Okay, so what I'm telling you is the magnetic field gets stronger as I get close to the wire. Because this is adding vectorially the Earth's magnetic field, which is north, and the magnetic field caused by the wire, which is in this direction. All right.
How do you know it's in that direction?
Well, because of this right-hand rule.
Yes.
Yeah, because I did the right-hand rule, and I figured out, oh, I'm doing contortions right now, but the tips of my finger are pointing this way. And so if I add a lot of this way and a little bit of that way, I get almost pointing due east. But as I go away, say half and half, and I get half this way and half that way, I get 45 degrees. And if I go up here, and if I got a little bit of east and almost all north, I get almost all north. What would happen if I put it under?
Oh man, I want to know.
All right, so I'm going to keep the same current, and this may be hard to see on the camera, but I'm going to tell you I'm pointing west instead of east. And why is that? Because we're talking about a magnetic field that goes circular. So if I'm pointing towards this part of the room above, I would expect to point towards that part of the room below. This is circular. Yeah, this is tough. Thinking 3D is tough, but you know what? Physics 102, you can do it. I know you can do it. And right now you are doing it. And this is great. And this is one of those things that Faraday looked at and thought about, and he was unique because he could kind of think not just in straight lines. Oh, it's going back to the point, whoops, I got to put it here. Okay, oh, I got her spinning. But he could think not only in straight lines, but he could actually think that fields could be curved. He didn't have the proper mathematical education at the time, and that turned out to be an advantage for him. Okay, so place the compass over wire A as shown in figure 2.2. Push down and switch was what we did. What did you observe? Good. Hold the compass about 1 inch away from it. This is where it decreased. Okay. Based on what you learned in the previous section, what do you think happened? Okay, now place it directly under about 3 centimeters. So we're holding it about 1 inch away. Don't push on the switch right now. So imagine there's no current. And instead of pushing on the switch, what we're saying, oh, I'm sorry, this is while the current is going. Pushing on the switch would turn it off. So the current is going right now, so we get a little bit of deflection. A little bit of west, plus a whole lot of north. The magnetic field of the Earth is staying the same, we're saying. What's changing is how far away we are from the wire, and the wire's magnetic field is being constant. And, oh, okay, I have messed up, guys. Now push the compass directly under wire A about 3 centimeters below the wire. Do not push on the switch. That is all Earth's magnetic field, so it should point straight north. Now hold the switch down until the compass needle stops oscillating. It's going to point a little bit to the west. And if we get really up close to that, then it's going to point a whole lot to the west. Okay. So in the table below, sketch the magnetic field above and below the wire. Above, I'm hoping you point towards the east. Below, I'm hoping you point towards the west. So when you're holding the switch down, what's going on here is you are turning the power on, the current is going through the wire. When you do not have the switch down, that means that you only get the Earth's magnetic field. So the compass should only be pointed to the north. I think that's good. And I think you can finish up that section. I'm going to turn the power off. And my compass is going to go back, pointing north. Hey, I have one more thing I want to show you. And now we're going to go a little 3D on you. And it's going to deal with the magnetic forces. Now, you've seen magnetic forces before because Dr. Johnson made things move. Now, what's the only way you can make a thing move?
Magic.
What's the only other way you can make a thing move?
I try to convince people I'm a wizard because wizard comes from the word wise. But
Tell me you're a magi. Because that comes from the word magic.
nice.
Well, magic maybe comes from. All right.
Well, I'm thinking fields.
Well, there are two different types of forces. There's either a contact force or there's a field force. And you had your magnet close to there, you weren't touching. So there's got to be some kind of a field. And the magnetic field will actually make a force and make things move. It's fantastic. And yes, we can draw free body diagrams if we really wanted to. Maybe not today. Okay, force. Now, you guys know the equation. Force equals QVB? Yeah, sine theta. Now, right now what I'm dealing with is, I'm not going to worry about theta because it's going to be 90 degrees. I have conventional current. So instead of QV, what I'm going to be doing is, my force is going to be I times LB sine theta. Okay. What I have here is I've got conventional current going up through red, coming down, going across, going up, and then back. Okay, so right now, for this portion right here, my conventional current is going to be going towards the camera. Good. And for my right-hand rule, my conventional current's my thumb. So I'm going to be pointing at you somehow. Okay. For my magnet, red is north. Fingers are my field. So if I'm going to go upward, then it's going to go this way. Okay. So my thumb is going to be pointing at the camera. My fingers are going to be pointing upward because my north is going upward. So my palm, just like Iron Man, is going to tell me where the force is. I think this guy is going to move towards me. It's very slight, but let's see. Is it on camera?
It's not, it's focusing on your shirt and not on the wire. There it goes, okay.
So I touched it that time. I didn't mean to touch it.
Oh, there it is. So cool.
Okay, so what I want to do next is, I want to flip it. So now I'm putting a south up there. The current is still going this way, but now my fingers are down. My palm is pointing this way. So as I come up to the south, I should be deflecting the other way, away from my body towards this way.
If we use the neodymium, will we get a better deflection?
Most probably. Do you know which one side's north?
The non-cap side, I believe.
The non-cap side.
You can check it.
We'll see. That looks like a better deflection for the north. We'll do it for the south. There's a cap on here, so maybe it won't be as effective. That's still pretty good. Hey, let's switch the direction of the current. Now, you may not be able to tell down here, but I'm taking my black wire and putting it into the positive.
Oh, we can tell.
And I'm taking my red wire and putting it into the negative. So now the current is coming up the black, going through here, across here, and down the red. So now my current is this way. Still use the same right hand. So my thumb is going this way. If I'm going to go north, oops, excuse me. If I'm going to go north, then I'm expecting my deflection to go towards the board. Oops, which I get. And with the really strong magnet, which I've attached to the metal base. Yep, getting a really good deflection. South. Okay. So there's two different variables here. One variable is the direction of the current, your thumb. It matters if I point this way or that way. Good. The other direction is the field. It matters if my field is north upward or south going upward. In essence, fingers pointing down. Yeah. Now, what about other forces? Well, the force that the left side gets, my left side gets, is counterbalanced by the right side. So that's why it's either swinging towards the board or away from me or towards me. So that's that. Okay. Whenever, sir.
All right, so thank you, Professor Ashcraft. That was outstanding. We wrapped up section 3. Now on to part 4 is quantifying this stuff. So that's all qualitative up to this point. We've made observations and observed how these interactions take place. Now we're quantifying it with a little bit of math. We get the shakes if we don't do math, right? We go through withdrawal if we spend an entire lab with no numbers. The last two parts of this within section 4, part 4, are just solving a problem. So I don't think you need us for that. I think you can do that on your own. But if you need help with it, you know where to go.